Hello, calculus students. In this online lesson, we will continue our discussion of vectors, specifically referring to the dot product of vectors or scalar product between two vectors. And we will also talk about parallelism, or how to tell if vectors are parallel. So, given two vectors, vector A and vector B, I've written them here in component form. Vector A has an x component as well as a y component, which we're calling a sub 1 and a sub 2. We can find the scalar product, or dot product, if you will, by simply multiplying a1 and b1, essentially finding their product, which is part of where the name comes from, and then taking a2 and b2, finding their product, and adding those two products together. That's called the scalar product or dot product. There's also something called the cross product. So we want to make sure that we are using this dot symbol, which we often use for multiplication, but obviously this isn't a straight multiplication problem because there's also the addition going on in there. Why is this useful? Well, we use the dot product as part of a formula that can essentially help us find a missing angle. A sub 1, b sub 1 plus a sub 2, b sub 2 is equal to the dot product, and the dot product is equal to, again, think about these absolute value signs. We know it's bold, so we know it's a vector. So that's magnitude of A times magnitude of B times the cosine of the angle formed by the two vectors. Okay, now how do two vectors form an angle? Well, if I have one vector going this direction, another vector going that direction, they have created this angle right here. I can find that again by finding the dot product and utilizing the magnitude of each of those vectors. A more common way to write that formula, which is probably found in your formula packet or something similar to it, is right here. Cosine of theta equals, and again, this is just the dot product. It could also be written A dot B. But here they've taken their two components. Again, the x components getting multiplied together, the y, and then we add those together. All divided by the product of the two magnitudes, which again came from our previous lesson. The nice thing about this is often we're trying to find right angles or perpendicular vectors. Again, a perpendicular vector is one that forms or two perpendicular vectors are ones that form a 90-degree angle. And we know that they're perpendicular if the dot product equals 0. The reason for that is because the cosine of 90 degrees, or the cosine of pi over 2, always equals 0. And if you look at this formula here, if this equals 0, what I just underlined, then all of this has to equal 0. But remember, we can't divide by 0, which means the numerator must be 0 here. So again, if it's a perpendicular, the numerator is going to be 0 of this formula, which means the dot product is 0. Very helpful because you don't have to do half as much work if all you're trying to do is find out if they're perpendicular. Just set the dot product equal to 0. So that brings us to this first question here. We are asked to find t so that these two vectors are perpendicular. Well, again, if they're perpendicular, that means their dot product equals 0. So I could say that A dot B equals 0 if and only if they're perpendicular. And for the dot product, we take the two x components and multiply those together. -1 times 2 plus the two y components, 5 times t. Again, that all should equal 0. Simplify, we get -2 plus 5t equals 0. I'm going to add the 2 to the other side, so now I have 5t equals a positive 2. Divide both sides by 5, and I see that t must equal 2/5 in order for these two vectors to be perpendicular. All right, on this next slide, we are given pairs of vectors and we're asked to find the angle between them. We're not going to do all these. We might just do this first one here. And again, feel free to work through the others or try them after my example. So we'll start with number one. We're going to use that formula again that says the cosine of any angle is equal to the dot product between the two vectors divided by the product of their magnitudes. So that's our formula here, specifically using A and vector B. In the later ones, all these A's and B's here would turn into C's and D's or M's and N's if we were on number 2 or number 3. So now all we need to do is substitute in some values. We're going to leave cosine theta alone for now. And A dot B, remember, we're going to multiply the X components together and then the Y components together. So we'll have 3 times 5 plus 4 times 12 all over the magnitude of these vectors. Now think back to magnitude. That's going to be a radical, and it's based on the Pythagorean theorem of the X and Y components squared and then added together. So 3 squared plus 4 squared would be the magnitude of vector A, and 5 squared plus 12 squared would be the magnitude of vector B. A whole lot of simplification. Now you could put this in your calculator all in one step. I wouldn't recommend it unless you get very careful with your parentheses. We can simplify here. We've got 15 happening in this first product, and then we've got 48 happening there. And so I believe that will be 63 in the numerator. And in the denominator, we've got square root of 9 plus 16, which is 25. And then here we've got 25 plus 144, which is 169. And I know the square root of 25 is 5. I don't have to worry about the negatives because that was built into the formula here. Unless you're writing the radical, you don't have to worry about it. So it's a positive 25. A positive 5 here. So we've got 63 over 5 times 13. 5 times 13 will give us 65. So we end up getting cosine of theta is equal to 63 over 65. Now we still haven't actually found theta. We still haven't found the actual angle between them. We found the cosine of that angle. Now, depending on whether you want your answers in degrees or radians, make sure your calculator's in the correct mode. Most of our work this year will be done in radians, but I'm actually going to put my calculator in degree mode just because I think it's something we're more comfortable with to think about at the moment. So in order to get theta alone, we need to get rid of this cosine here. So we have to do inverse cosine of all this and inverse cosine of that. So our inverse cosine and cosine cancel out, leaving just theta, or our angle. And then we'll use our calculator. Inverse cosine of 63 divided by 65 gives us a relatively small angle of 14. Approximately 0.3 if we round to 3 significant figures. And that would, again, be degrees. So that's the idea. It combines a lot of things that we've seen throughout this this chapter. Defining the vectors, using the new dot product here, doing some magnitude work, and then going all the way back to last year with trig and things like that. Another similar example, we have vectors A and B. They have lengths of 5 units and square root 7 units respectively, and the angle between them is 110 degrees. Find A dot B. So first and foremost, let's set up our formula. We know that cosine of any angle is equal to the dot product divided by the magnitude of those two vectors. multiplied together, or their product. So let's start doing some substitutions. We know that the magnitude of A is 5, and we know the magnitude of B is square root 7. And then we've got cosine theta here, but I don't actually know cosine theta, but I do know the actual value of theta. It's 110 degrees. And again, we're treating A dot B as our only variable. So at this point, we just have one variable left, so we can do some algebra to solve it. We're trying to get that alone. So the only thing that's keeping A dot B from being alone is all this stuff here in the denominator. It's being divided, so let's multiply the square root, 5 square roots of 7 to both sides, which will cancel out here. So then A dot B is equal to all of this stuff, which we can just throw straight into the calculator. And we've got 5 times square root 7 times cosine of 110. And I get an answer of negative 4.52. And it is totally possible to have a negative dot product. The last part of our lesson, we're going to look at parallelism. In order for vectors to be parallel, they go in the same direction. They don't have to be equal. Again, equal vectors have components that must be the same. Their x and y components must be exactly the same. And so to visually represent that, if two vectors are equal, they're going in both the same direction and they have the same magnitude or visual length. But if they're parallel, then one's a scalar of the other, meaning they're going in the same direction, but they don't have to be the same length. Which means that there's some scalar or some constant that I could multiply by 1 to turn it into the other. Again, if it's a bigger one that we're turning into a smaller one, that constant could be a fraction or some value less than 1. And if it's a small one that we're turning into a bigger one, it can be, something larger than 1. That scalar we'll refer to as k. We're still using these double lines to show that the two vectors are parallel, just like we would for lines in geometry and such. So let's take a look at one last example involving this. Again, we'll just look at one of these. But if the following vectors are parallel, that means there's some scalar that I could use to multiply by 1 to turn it into the other. So I'm just going to focus on the x components, because in this one, that's all I know. So I know that there is some scalar that I could multiply the 3 by that would turn it into the 12. So what would that be? Well, divide both sides by 3, and I see that k must be 4. So there's some scalar 4 that I could multiply by both the x and the y component to turn it into my new vector. Well, we can check it. 3 times this 4 does in fact give me 12. Therefore, right here I can see that 5 times this same scalar here of k equals 4 should give me my final answer of t. So t is equal to 5 times my scalar of 4. So t equals 20. Homework will be found on page 306, 310. Please bring in any questions next time for class, and good luck, ladies and gentlemen.